Welcome to the massive open online course on Aspen Plus. To continue with this lecture series on basic process modeling, today we will discuss about the columns. If you look at the Aspen Plus simulation window, you will find various types of columns to operate: DSTW, DISTL, RADFRAC, extract, multifrac, SCFrac, petrofrac, and concept. We'll go one by one. DSTW, it says it is shortcut distillation design using the Wien underwood Gilliland method. The second one is DISTL. Again, it is shortcut distillation rating using the administer method. Third one is RADFRAC. It is used for rigorous 2 or 3 phase fractionation for single columns. It can model absorber, stripper, etc. Extract model, it is for rigorous countercurrent extraction of a liquid with a solvent. It can model liquid-liquid extractor. And we have 4 more. The first one is rigorous fractionation for complex columns such as crude units. The second one is shortcut distillation for complex columns such as crude units and vacuum towers. The third one is petrofrac, that is rigorous fractionation for petroleum refining applications such as pre-flash towers. And finally, it is concept. It performs feasibility and design calculations for distillation column. So you can understand that these 4 are mainly for crude and they are principally used in petroleum industries. Obviously, they are for advanced users and they are not within the scope of discussion in this lecture series. So in today's lecture, we will limit ourselves within the first 4, that is DSTW, distill, RADFRAC, and extract. First, we begin with DSTW. As said, is simple shortcut distillation to estimate parameters to achieve desired separation. It uses Wien underwood Gilliland method. It takes 2 assumptions. One is constant molar overflow, another is constant relative volatility between the light and heavy keys. Now, Wien, that is the Fenske equation, it determines the minimum number of stages and the optimum feed location at total reflux condition. Whereas Underwood equations, they determine the minimum reflux ratio, and the Gilliland correlation that determines the actual number of stages and the feed location at actual reflux ratio. So we shall learn the DSTW block and its efficacy with the following example. So this is the example of simple distillation exercise. So this is a column. The feed contains a mixture of methanol and water. Its flow rate, the weight fractions, pressure, they are given. And also it is said that feed is saturated liquid. Temperature is not given, but it is said saturated liquid. That means the vapor fraction is 0. So this information is needed for the simulation purpose. The distillate contains 98.1% of methanol, whereas the bottom product contains 7.7% of methanol. Both condenser and reboiler, they operate at 1 atmosphere pressure. The reflux ratio is 1.3 times of the minimum reflux ratio. So with this information, we will use the shortcut distillation method using Wien underwood and Gilliland method. So let us go to the simulation window. First, we have to go to the properties and we have to enter the components methanol and water. Press next. We shall use the inertial RK method, which is inertial Renon with Redlich-Kwong equation of state with Henry's law. We'll use this because for methanol water system, this is the best property method that we can have. Press next, run, go to simulation window, go to column, take this DSTW, connect the material streams, rename them, write it as feed, write it as DS dist, DS for the DSTW, DS bot. We are using this prefix DX because we are going to use the distillation RADFRAC also and compare. Press next. It will ask for input for feed material. So we have the information. It is at 18.4 psi and vapor fraction 0. So 18.4 psi, vapor fraction 0. The feed rate is 120,000 pounds per hour, mass flow rate. So we are using English unit. So convert it in 120,000. Mass fraction, methanol is 36.88% and water is 63.28%. So first one is 0.368 and then 0.632. 0.368, 0.632. So total it comes 1. We have to change it to mass fraction. Press next. Here it is asking for the inputs for the block B1 running with DSTWU. So you can either specify number of stage or you can specify reflux ratio. Now we have the information of reflux ratio, not the actual reflux ratio, but we know that reflux ratio is 1.3 times of the minimum reflux ratio. Here in the reflux ratio, if we write 1.3, then the actual reflux ratio will be taken as 1.3. But if we write minus 1.3, then minus indicates that we are referring to 1.3 times of the minimum reflux ratio. So that's what the prefix minus means over here. It is not negative sign. It is 1.3 times of the minimum reflux ratio. That's what it means. The condenser and reboiler, both of them operate at 1 atmosphere pressure. So for both of them, we write 1 and 1. The light key component, obviously it is methanol, and recovery is 98.1%. So we write here 0.981. The heavy key is obviously water, and here the methanol recovery is 7.7%. So it is 0.077. So here it is 0.077. So the specifications are complete. Now it is ready to run. Let us run. The results are available. Let us see the results first. So here the minimum reflux ratio has been calculated as 0.607989. So this is system calculated minimum reflux ratio. Here the actual reflux ratio is 1.3 times of the minimum reflux ratio. So if you multiply this with 1.3, then you will definitely get 0.79385. Minimum number of stages is 4.62 and the actual number of stages is 9. Actually it is saying 9.00 because it is calculating that way. In reality, number of stages cannot be fraction, so we should take 9. Feed stage is 5.47768. Now here also we have to take 5 for actual operation. Reboiler heating required is in British thermal unit, it is given in BTU by HR, but we can change this unit to say megawatt. It is 14.026 megawatt of duty is required for this reboiler, and condenser cooling required also is around the same 13.8302 T. 13.8302. Distillate temperature and bottom temperature both are given. The bottom temperature, obviously, it should be near to water boiling point. And here another important information is distillate to feed fraction. It is almost 0.3. This information will also be required in future calculation. Now let us see the stream results. So these are the stream results. This is bottom product and this is distillate product. Here you can see the total mass flow rate is 1200. In the distillate we have 49,160, rest is going as the bottom. Now the methanol content is 43,321 in the distillate. Only 839 goes to bottom. Whereas water, out of 75,840 pounds per hour, 70,000 goes to bottom. Only 5,839 goes at the top. So these informations will be required for us in further calculation. The next one is DISTL, distill. It is another shortcut distillation to estimate the parameters to achieve desired separation. And one can confirm the results obtained through DSTWU. It uses the administrators method and it also assumes the constant molar overflow and constant relative volatility between the light and heavy keys. And to operate, it needs these following data. It needs actual number of stages, the feed location, the actual reflux ratio, and the distillate to feed molar ratio. It also needs the condenser type, whether it is total or partial, and it also needs the operating pressure of condenser and reboiler. So all these information we already have from our previous calculation of DSTWU. So now we will solve the same simulation problem using DISTL, not with DSTWU. But we will not delete the DSTWU simulation because we need this information in our next simulation. So let us go to our next simulation. For that, let's go to main flow sheet. Here we do not delete the previous simulation. We will just copy. Now we do not want to delete this part because we need it. We just make some cosmetic changes over here. Here we rename it as DISTL, distill block. Now we will use a manipulator over here this is a duplicator. So this duplicator block, it just duplicates the streams as if the same stream is going in two different paths. So for that, we have to connect with this and then material feed to this one, material feed to this one again, outlet and outlet. So we rename it as DI dist and this one is DI bot. Then we put next. Obviously the feed information has already been given. It is just duplicated. Now we have to give the information on the distill block. So here in the distill block, we need to give the number of stages. So the number of stages, already we have this information over here. So number of stages is 9. So we just give this information 9. And remember, we have to give a whole figure. We cannot give 9.04 because it is actual number of stages. Feed stage, same information is there. Feed stage is at 5.47. So we'll give 5. Reflux ratio 0.790385. 0.790385. Distillate to feed molar ratio 0.299958. So we can write it's 0.3. Not a problem. Condenser type is total. Pressure, again, it is 1 atmosphere, 1 atmosphere. We run it. So our results are available. Now we will see this result. Check the condenser duty first in megawatt. It is 13.831, slightly lower than the previous one. And reboiler is 4.0285. Earlier we had 14.026 and here we have 14.0285. Almost same. Now obviously we are interested to know the stream result. So let us write here ds dist. In place of ds dist, we'll write di bot over here. So the bottom product of dstw block and distl block, they are written side by side. The same arrangement can be done for distillate also, so that we can compare it better. Here again we see there's slight difference between the methanol production in the distillate. Using distl, the quantity is slightly higher. Obviously here we are not actually in ideal condition, we are doing it in the real condition. In dstw block, we used the information in fraction form. The number of stages was fraction, the feed stage was fraction. But here it is actual, so it is 9. It's a whole figure, 9, 5, etc. So the final result will be slightly different. Now we will understand the limitations of DSTW and DISTL block. Both these blocks are very useful for obtaining first approximation of the column parameters, because these models are based on assumptions of constant relative volatilities and constant molar overflow. So thus their results are not very accurate. Therefore, the next natural step is to use these column parameters and use them in more rigorous mode. And what is the more rigorous model? We have RAD-FRAC. So the next thing that we are going to do is using RAD-FRAC model to solve this problem. We have to use now the RAD-FRAC model and compare with the previous two. So for that, we again go back to main flow sheet, pull it down over here, this RAD-FRAC, connect the material streams. This is outlet, distillate, this is bottom. Write it as RAD-FRAC dist and RAD-FRAC bot. Press next. It will ask for the column parameters. Here, the calculation type, it is suggesting equilibrium. Now, two types of calculations we can do, equilibrium and rate based. We will do one by one. For this calculation, we will use only equilibrium model, but later we will see the rate based calculation for some other problem. Number of stages we have to give 9. Condenser is obviously it is total condenser, no vapor fraction. Reboiler we can use either kettle type or thermosiphon type. Let us keep it as kettle type. And we have to give this operating specification, either of two. So we have distillate rate, bottoms rate, reflux rate, boil up ratio, and others. Let us use distillate to feed ratio because this information we already have from our shortcut calculation. So distillate to feed fraction is 0.3. So we will use this information over here, 0.3. 3. And reflux ratio, that also we know, it is 0.790385. So here, all the information that we have got from shortcut distillation. So shortcut distillation block is very useful for giving you the first approximation of this. We can fine tune it later. Streams, the feed stream, the location of feed stream, we know it is stage number 5 on stage number 5. So not above, it is on stage number 5. Then you have to give the pressure. Obviously the condenser pressure, it is asking for condenser pressure, which is 1 atmosphere. We already know it from our problem. So the simulation is ready to run. Here the stage 2 pressure and stage pressure drops, they are optional information you can give if you have the information. Even if you do not have, no problem, the simulation can run either way. So now you can run the simulation. Simulation results are available. So let us see the simulation results. Here you can see heat duty in watt. Let us use megawatt, it is better. The condenser is 13.8491 megawatt. DSTU shortcut, it was calculating as 13.83. This is calculating as 13.84, almost same. The same thing will be there for reboiler also. Heat duty is 14.04. Now we are interested to know the stream results. So here we will take rad frag bottom. Here we take DS dist, then DI dist, and here we will say rad dist. Again, you check the mass flow rate. Methanol 0.015717, all of them are same. Okay, slight difference will be there because one is rigorous calculation and another is shortcut calculation. These differences will be inevitable. Now, this can do much more rigorous calculation because you can design the column internals. Till now, we were not doing any mechanical design of column internals. But with radfrac, we can definitely do it. Let us say how. Here, you have the option for column internals. So you can add column internal, generate. So here, you have the internal. So a pictorial form of column is demonstrated starting from stage number 2 to 8 because we have 9 stages. Stage number 1 is condenser, stage number 9 is reboiler. So rest of the stages are from 2 to 8. The feed stage is 5. Now we have to add a new section. You can design the upper section and lower section separately, or you can design them together. Let us design them together. We should not complicate the matter. So we'll say add new. So this is the section number 1. We start at stage 2 and end with stage 8. Now here we have the option of interactive sizing as well as rating. The beauty of interactive sizing is if you give very little information, Aspen Plus, based on its inbuilt data and information, it can calculate and suggest you some column internals. And those column internals can be suggested and viewed by pressing these details. Now, internal type, it is trade, it can be trade or it can be packed. For the time being, let us choose trade only. Tray type, it can be sieve, it can be bubble cap, and lot many other types are there. For the time being, let us choose sieve. Tray spacing and diameter, it is suggesting, the Aspen Plus is suggesting this dimension. If you view the internals more, it will give you further information. That is, what is the whole area? If this is the sieve, then whole area per active area is 0.1. You can choose number of holes also. What is the side downcomer width, top and bottom, side wear length, wear height, downcomer clearance, diameter, tray spacing, everything is being suggested by Aspen Plus itself. You do not have to give any information. Aspen Plus can do the simulation with this. Later, if you are not happy with the final result, you can do the fine tuning over here. But let us assume that these are correct and you are happy with this. Let us run the simulation. So the simulation results are available. So these are the column hydraulics. It says that total height is 4.26 meter. It's a column height. total head loss this much, total pressure drop, number of trays per packed stages is 7. All this information, total residence time, everything is given over here. And column internals, you can again view it and you will find the tray type, tray spacing, and the limiting condition of all of them. Now this limiting condition is very, very important, and you can further scrutinize them by seeing this hydraulic plot. It is very important. If you go and check the hydraulic plot, you will find that not all the trays are good. The tray condition is pictorially given by this. Now here if you see, say fifth tray, this is the constant V by L line and operating point is over here. So this is the area where your operating point should lie at each and every stage. It should not go higher than that because this is the maximum entrainment line. It should not go beyond this because it is weeping line. This is 100% weeping, dumping line. This is the minimum wear load. This is maximum wear load. So all these are written over here. What those lines they mean. Each and everything is written. So you can go through them. Now here we can understand that stage number 5 to 8, they are good. But 2, 3, 4, they are not good. So we find a cross mark over here. So what we will do, we will go and check what is the problem. The problem is in this tray, say number 2, the operating point is over the maximum entrainment. So there is a condition of flooding over there. So we have to reduce the flooding. So the best way of reducing the flooding is to increase the diameter, right? So let us increase the diameter of the column. So go back to geometry. Here we have the diameter. So let us use 3 meter and see what happens. Let us run the simulation once again with this diameter. So run is complete. Now we go back to column hydraulics once again. Now it is fine. The entire column is blue. Earlier the top portion was red. Now each and every point. So this is the tray number 2, which is coming within this. 3 also is coming within this. 2, 3, 4, 5, 6, 7. Everything is within the limit of entrainment. Okay. So the column is running fine. So here we see starting from 2, 3, 4. Earlier we saw a cross mark for first 3 trays. Now the cross mark has gone because the operating point has come down from here to here. So like that, you can check the hydraulics and other matters. In this section, we assume tray column. Instead, we can use packed column also. Now, if you assume packed column, then we have to see the packed height also. What is the section packed height? Let us say we will use 5 meter of packing and check whether our simulation runs good. So run it, okay? The simulation has run. Let us go back to see the hydraulic plot. Yes, so the operating point is within the limit. So this is the minimum liquid rate and this is the, so here it is minimum pressure drop per unit packed height, the dotted line. So it is way above the minimum pressure drop. And this line is allowable pressure drop per unit packed height. So it is way below that. And this is the minimum liquid rate. So that is also met from the very first tray. So 2, 3, 4, all the trays, they are meeting the criteria. So this is how you can do the design of packing. Now the packing material also you can check. Here the packing characteristics, we are using generic model. We can use Raschig ring with ceramic material. Dimension we can check. The packing size also we can check. And many other parameters we can change and rerun the calculation to see what is the final output. Okay, so that is how you can do the simulation with RADFRAC, and that can be rigorous calculation. Now we can summarize the features of RADFRAC block. It is a rigorous simulation block for absorption, stripping, extractive distillation, azeotropic distillation, and reactive distillation. It can handle highly non-ideal components. It can have multiple feed and product streams. It can differentially simulate a column with trays, random packing, structure packing. In the multi-stage vapor liquid calculations, it can do for reboiled absorption and reboiled stripping as well, in addition to ordinary distillation, absorption, stripping. It is suitable for two-phase system, three-phase system only in equilibrium mode. It's suitable for narrow and wide boiling system. It can model columns in which two liquid phases and chemical reactions occur simultaneously using different reaction kinetics for two liquid phases. And you know that chemical reactions can occur in distillation, that is called reactive distillation. It can model both random and structured packing. A few glimpses have already been demonstrated. And it can also calculate the size and rate columns consisting of trays and or packings. Now, it is not possible for me to demonstrate each and everything, but I will cover two things. One is absorption column and another is the reactive distillation. These two things will be covered in the next few slides. First, we'll take the example of reactive distillation. Now, this is a column in which acetic acid and ethanol are fed in a column of 23 stages. The acetic acid is sent at 8th stage. Ethanol is sent at 14th stage. Their flow rate and temperature pressure conditions are given. The condenser operates at 1 bar pressure and reboiler duty is given 0.7 kilowatt. The reflux ratio is 3. And as it is reactive distillation, obviously these two components, they react with each other and form ethyl acetate and water. So these two things are product. So the reaction through which these two are produced is this one. Now we will model this through RADFRAC. For that, let us open a new simulation. So we have first component acetic acid. We can write in this fashion. This is acetic acid, water, ethanol, and then ethyl acetate, find ethyl acetate. So this one you choose, add selected compound. Let us rename it as ETH-S. Press next. We will use unifac method because that is the best property method for this kind of system. Run it. Go to the simulation block. Bring in the RADFRAC column. Connect the material first. Feed, distillate, product. Rename it as feed, dist, bottom. Now here we have two streams. So instead of feed, we should write acetic acid and we have to look for a second feed through which ethanol will be passed. Now go to next. Yeah, acetic acid input. For both acetic acid and ethanol, the flow rate and temperature pressure conditions are same. Flow rate is 0.05 liters per minute standard volume and temperature 25 degrees centigrade, 1 bar pressure. So we have to add in these values. So 25 degrees centigrade, 1 bar standard volume flow rate of 0.05 liters per minute. Next is ethanol, the same information, 25, 1 standard volume flow, 0.05 liters per minute. Press next. It will ask for the specification of RADFRAC. Again, it is equilibrium model. Number of stages is given, 23 stages. Condenser, total condenser, and here two information are given. One is reboiler duty, another is reflux ratio. So reboiler duty 0.7, reflux ratio 3. So we will use reboiler duty as 0.7 kilowatt and reflux ratio is 3. Okay, total condenser, somehow it has been deleted. Right. Then go to streams. Acetic acid is given at the 8th stage, ethanol is given in 14th stage. So it is 8 and 14 on stage, on stage. Then we have pressure. Condenser pressure is everything 1 bar. Yeah. So now the equations are all balanced. It is ready to run. Now if we run it, let us see what happens. Yeah. So run is complete. We can see the result. So this is the stream result we have. Here you can see that there is no trace of water in the distillate and there is no trace of ethyl acetate in distillate and bottom either. None of these water and ethyl acetate they are in the distillate and bottom. Why so? Because we have never indicated that there is a reaction that is happening. In the inlet, we have given only the acetic acid and ethanol. We have not entered water and ethyl acetate. So there is no water and ethyl acetate in distillate and bottom product because we have not stated that there is a reaction going on. We have to state that there is a reaction going on. Then only Aspen Plus will understand that it is a reactive distillation. So for that, we have to make certain changes. So let us go back to setup, and here we have to add a reaction. So that reaction begins at stage number 8, where acetic acid is being fed, and it ends at 14 because acetic acid is being fed through the 8th stage, whereas ethanol is being fed through 14th stage. So all the reactions are expected to happen between 8th stage and 14th stage. There is no reaction ID as such, so we have to create a new reaction ID. Let us say R1. Then you will find over here the reaction. You have to add a new reaction over here. So it can be kinetic, equilibrium and conversion. For the time being, let us take an equilibrium reaction. So it reacts component acetic acid with ethanol. They produce ethyl acetate and water. Here the coefficient is -1 and -1 because they are reactants, and here the coefficient is 1 and 1 because they are product. Press next. Now the reaction is defined. Let us run. Now the result is complete. You see how much of water has been produced. This together it is 0.03488 moles, kilomoles in the bottom, and 0.0058 kilomoles per hour in the distillate. Similarly, you can combine. This is the amount of ethyl acetate that is being produced. If you want to see the mass flow rate, nearly 3.5 kg per hour of ethyl acetate and 0.7 kg per hour of water has been produced through this reactive distillation. Till now we were doing only equilibrium based calculation. Now we will see how the rate based calculations are done. In rate based simulation, the column can be designed and analyzed completely without the recourse to any theoretical stages, spray efficiencies and height of transfer units. You can literally take a ruler and measure the height in feet and meters and give that information to Aspen Plus, and it can calculate on the basis of rate. Mass transfer rate models are used. Mass transfer coefficient, gas liquid, contact areas, concentration difference, driving force, these are used. And the good correlations for film coefficient and measured equipment geometries like wear heights, passes, open area on trays, random packing, size, brand, crimp angle, crimp height of the structured packing, etc. These kind of geometries, they allow the performance of a real tray or a given depth of real packing to be predicted. To understand that, let us take an example of absorption column where rate-based simulation can be done. Let us take this unit. Here we have a packed column where gas containing 97.4 mole % of air and 2.6 mole % of acetone, flow rate and temperature pressure condition is given. This gas is being passed to this column and it is scrubbed through water, pure water, whose flow rate and temperature pressure conditions are given as well. Column is operating on rate based at 1 atmosphere pressure. It has 10 stages. Its height and diameter are given, 2 meter and 0.5 meter. There are some packing information, 1.5 inch Raschig ring, generic vendor, ceramic material, all these information are there. Let us try to simulate it. For that again, we have to open a new simulation. So we have here air, acetone and water. We'll use simple NRTL model. Next. Run it. Go to simulation. Now here although you are using RadFrac, but this kind of icon is not very suitable for you because this icon has condenser and reboiler units with it. Instead, you can use an icon of this nature which doesn't have any condenser and reboiler. So you are using the same model but with a different icon. It is just a cosmetic difference, nothing else. All the prevailing equations with the rad frac, they remain the same. So we have to add in the material. So there are two inputs. One is for gas in and another is for water. There are two outputs. One is for vapor or gas out and this is the liquid out. So we name them accordingly. We'll write it as gas in and gas out, and this is water and this is liquid. So we will place this equation over here. So this water, we will bring it over here. And gas in will pass from here. There is no hard and fast rule that you have to do in this manner, but these cosmetic changes will make the simulation look better. Okay. Now press next. So it is asking for inputs for gas in. So we know it is air 97.4. So air and acetone 0.974, 0.026. So it is 0.974, 0.026. They are all mole fraction. And temperature 25, pressure 1 bar, and molar flow rate 14 kilomole per hour. Next it will ask for water. Yes, water it is asking. The temperature and pressure remains same. And water is 45 kilomole per hour. Press next. Asking for the specification for the rad frac. Here we will use rate based. Number of stages, 10 stages we have. There is no condenser, so we have to say none. And there is no reboiler, so we have to say none. So as there is no condenser, no reboiler, so operating specifications are not required at all. So go to streams. Gas in, obviously it has to be sent from the bottom. So it is 10 stage, on 10 stage, and water has to be given from top. So above, and this is on. Go to pressure. So here it is not condenser but stage 1 pressure, which is again 1 atmosphere. Now go to next. It is asking for column internals because the rate based calculation always asks for the column internals. You have to give the length and breadth of all of them. So it is again 1 to 10 stages. Add a new section. Starting section is 1 and end stage is 10. It is rating internal type packed. Packing is Rastig ring, 1.5 inch Rastig ring, generic vendor, ceramic material. So we say Rastig ring. Generic vendor, material is ceramic, and dimension 1.5 inch. And then packing, it is said 2 meter height and diameter 0.5 meter. So section packed height is 2 meter and diameter is 0.5 meter. So the informations are complete. We can run the simulation. Now we have to give the rate-based modeling. Now here we are yet to give rate-based setup. Go to the section, all these internals, we have to say rate-based calculation. Yes. Okay. Now it is complete. We can run the simulation. Yes. So we ran it. Now go to the result section. So these are the stream results. You can see molar flows. Acetone, out of 0.364 kilomole per hour, 0.287 has gone into the liquid. It has been absorbed in liquid. Only 0.076 kilomole that is going in the gas out. If you see the mole fraction, so this is the amount going in the liquid. And the liquid, 99% is water, and in the gas out 96.3, sorry, it should be 99% only because 0.001 is only in the liquid. So 0.963 kilomole per hour. So gas out consists of mainly air and liquid consists of only water. Almost everything has gone into, you can see the mass flow, it will look better. Out of 394, 393 kg per hour has gone into the gas out for air. Acetone was only 21 kg per hour. Out of that, 16.69 kg has gone into the liquid. Only 4.45 kg is going into the gas out. Okay. Now our job is not complete. We have to see the hydraulic plot and understand whether there is any flooding and all. Well, all the trays are in bad shape. The entire column is in red. And the operating point, you can see the operating point is here. And this is the bottom line. What is this? This is the minimum pressure drop per unit packed height. That means none of the section of the column, it is having this minimum pressure drop per unit packed height. So to increase the minimum pressure drop per unit packed height, we can change something in the geometry. So go back to the column section. Instead of 0.5 meter, let us take 0.49 meter and see whether the simulation changes. Okay, no, it doesn't. Go back again. Instead of 0.49, let us say 0.45. Slight changes are observed. Let us try more. 0.4. Yes, so stage 1 is, it has come within the limit. Stage 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, entire column is now within. So this is the crux. You can change it further if you want. You can use 0.35 and let us see where it goes. Perhaps it will go in the middle. Yeah, it's much better for the entire column. So that is how you can play around with the column internals to see how far we can avoid flooding, and all those mechanical problems can be solved. Finally, we come to the extract model. The extract model is used for counter current extraction. Here we have to mention the number of stages. We have to give the thermal options, either adiabatic operation or stage-wise profiles for temperature and heat duty. And the key components have to be mentioned in the extract phase or in the raffinate phase, referred to as first and second phase liquid, and the pressure profile needs to be mentioned stage-wise. So to understand it, let us take the example for simulation of an extraction column. In the extraction column, we have a column having feed of a mixture of N-heptane and benzene, whose flow rates are 300 pound moles per hour and benzene 100 pound moles per hour. Pressure and temperature are given. The solvent is a mixture of dimethyl formamide and water. Their flow rate and temperature is also given. The column is operating adiabatically using unifact property method with 5 stages. The key components are, the first liquid is N-heptane, for second liquid is benzene. So to do that, we open a new simulation. So we have heptane, benzene, water, and dimethyl formamide. Yes, this is the one. So let us rename it as diform. Press next. We have to use the unifact method. Press run. Go to simulation. Take the extract block over here. Material in, material out. So here you have to write feed. At the top, this solvent, this is extract, and this is raffinate. Press next. Feed material, temperature 20 degrees centigrade, pressure 20 psi. All the units are in English units, so let us use ING. So pound moles per hour. Feed heptane 300 and benzene 100. 300 and 100. Next, it is 20 degrees centigrade, 20 psi, solvent, dimethyl formamide 750 and water 250. 750 and 250. Now we will use unifact method. Press next. Now we have done the property analysis, but we have to check whether the separation through extraction is possible in the first place. For that, we have to get the ternary diagram. So this is the ternary diagram. Let us take water as the component 1, dimethyl formamide as the component 2, and benzene as component 3. Run the analysis. Yes. So we have ternary diagram for water, dimethyl formamide and benzene, and by watching this ternary diagram, we can be sure that the extraction can take place. So number of stages is 5, and thermal option is adiabatic. We can specify temperature profile and heat duty profile as well, but we are not going through that complication. Let us choose adiabatic thermal option. Key component for first liquid, it is N-heptane, second liquid is benzene. So first liquid is heptane and second liquid benzene. Press next. The pressure in the first stage, it is 20 psi. Let us now run the simulation. Okay. You have to estimate the temperature also, stage 1 and 20 degrees centigrade. Now we can run. Yes. the results are now available. So you can see the stream results. So out of 300 pound moles per hour of heptane, 239 has gone into raffinate, only 60 has gone to extract. Whereas in benzene, in case of benzene, out of 100 pound moles per hour, 99 has gone to extract. So benzene has almost completely been extracted over there in extract phase. Obviously diform is the one which has extracted over here. The entire mixture has taken benzene out of it. So benzene has been extracted from the component. And the raffinate, it contains only, almost it is free of other things. 239.709 of heptane has gone into the raffinate phase. So that is how the extract model can work. So to summarize, in today's lecture, we have learned how to use DSTW, DISTL, radfrag and extract. These two are for shortcut distillation. This is for extraction, and this radfrag is the one which we have learned very thoroughly. We have not only checked the result of radfrag along with this shortcut distillation method, but we also have done some calculation for reactive distillation and rate-based absorption column with this radfrag. So I hope this exercise will be very much helpful for you to carry out your own simulations. Thank you.